So the last lecture that we did, we were talking about pulling forces. And pulling forces are, we're usually dealing with cables. And one thing that happens with cables pretty often is that they go over pulleys. So now we're going to talk about cables and pulleys. And I want to point out that the calculations that we're doing are for weightless cables. And massless, frictionless pulleys. So what percentage of the time are you dealing with cables that don't have any weight or pulleys that don't have any mass or friction? 0, that's correct. But often it's a good approximation. Okay, often you get good results by making this assumption, and so this is what we're going to do. And so the key to understanding what a pulley does is a pulley only redirects a force. It doesn't change the tension in the cable. It doesn't change the magnitude of the force applied to objects by the cable. It only changes the direction. Okay, so here's an example. So say you have a pulley hanging from the ceiling. The 10 kilogram mass and a 6 kilogram mass. And say we want to calculate the acceleration vector of the 6 kilogram mass. Well, one thing that we have to notice as we're going through this is there's a relationship between the motion of the 6 and the 10. Okay? What happens if the 6 kilogram pulley goes up 2 inches? What happens to the 10 kilogram? It goes down 2 inches, right? That's just how it has to be if that cable isn't going to change length. And so, because the positions have that relationship, you could think, one way you could think of that is that the position of the 6, yeah, let me write it like this. So the y position of the 6 is equal to the negative y position of the 10 plus some constant. Okay? That's just saying what I just said as an equation. And so you can take the time derivatives of both of these and you get that the y velocity of the 6 is equal to the y velocity of the 10. Take the time derivative again and you get that the y acceleration of the 6 is equal to the negative y acceleration of the 10. Okay. With pulley problems, you're almost always going to look for some kind of relationship like this between the velocities and accelerations. always need to recognize the relationship between accelerations. And that just comes from the geometry of the problem. Okay, so in this case, if the acceleration of the 6, if we're going to call that 0a, okay, we don't know what the magnitude is, but you can look at it and tell the acceleration is going to be up. Then the acceleration of the 10 is going to be 0, negative a. Okay, if that a surprises us and comes out to be negative, it'll come out to be positive here, so that relationship will still work. Okay, so let's go through this calculation. We're trying to relate kinematic quantities with forces. And so we're going to use Newton's second law. So the free body diagram of the 6 kilogram box looks like this. There's a cable tension. And then there's a downward force of 58.86. And so Newton's second law says 0t plus 0 negative 58.86 is equal to the mass, 6 kilograms, times our expression for the acceleration of the 6, that's 0a. The first equation says 0 equals 0. That doesn't help. But the second equation says t minus 58.86 is equal to 6a. Can we solve that? Why not? Yeah, that's one equation with 2 variables. So we're going to hang on to this and set it aside. We need another equation without adding any more variables if we're going to solve this. So now let's look at the free body diagram and Newton's second law for the 10 kilogram. Okay, so there's the weight. That's 98.1. And then there's a force applied by the cable. What's the direction of that force? It's a pulling force. Up. And what do we know about the magnitude of that? So this is where what pulleys do comes into it. We've already called the cable force applied to the 6 T. And so the magnitude of the force that same cable applies to the 10 also has to be T, since all that cable is doing is going over pulleys. Okay? All pulleys do is just change the direction of forces. Okay? So the magnitude here is T. Any questions about that? So Newton's second law says 0t plus 0 negative 98.1 is equal to 10 times 0 negative a. Remember that representation for the acceleration comes from the geometry. So we get a third equation that says 0 equals 0. and a fourth equation that says t minus 98.1 is equal to negative 10a. So now we can combine these two equations. Let's take equation 2, equation 2 and subtract equation 4. So t minus 58.86 is equal to 6a. And then the negative of equation 4 says negative t plus 98.1 is equal to positive 10a. And so you get 0t plus 39.24 is equal to 16a. So can someone divide that? What do you get for a? .45, leave it there, meters per second squared. So the acceleration vector of the 6 kilogram box you get from plugging this variable value back into our expression for acceleration that we had, this right here is the acceleration of the 6 kilogram box. We just didn't know what a was yet, and now we do. So this is equal to 0, 2.45. And so what's the acceleration vector of the 10 kilogram box? Yeah, in the 0 for x, negative 2.45 for y. That's this one, once we know what that variable value is. Okay, so here's another example. Say that you have a cart rolling along a flat surface. This is 5 kilograms, and it's attached over a pulley to a 2 kilogram mass. And we want to know what's the acceleration vector of the 5 kilogram cart. Okay, so what's the relationship between these two accelerations? They have the same magnitude. Yep. Yeah, that's right. So if we call, so if we say that the acceleration vector of 5 is going to be a0, then we know that the acceleration vector of the 2 is going to be what? Very good. 0, negative a. Because if you go in the positive x direction with the 5, that 2 goes in the negative y direction. Okay, that's the way it's, think of it as like, if this goes 1 inch in the positive x, where does this one go? It has to go 1 inch in the negative y, and so that's the relationship that you get. Okay, so Newton's second law for the 5 kilogram box. We have a weight of 49.05. We have a pushing contact with the ground, that normal force, I'll call that N5. And then going around the boundary, the only other place that there's contact is the cable tension T. I wrote Newton's second law. That's really the free body diagram. And so Newton's second law says 0, negative 49.05 plus 0 N5 plus T0 is equal to the mass times the acceleration of 5, which is A0. Equation 1 says T is equal to 5A. Equation 2 says negative 49.05 plus N5 is equal to 0. We don't care about these normals. There's nothing in the question that asks about that, but this one is going to be useful. So we'll set that one aside. And then go to a free body diagram of the 2 kilogram. So there's a weight of 19.62. And which way does that force vector go from the cable? Up. Yep. It's away from the chosen body because it's a pulling force. And what's the magnitude of it? T. So Newton's second law says 0T plus 0, negative 19.62 is equal to the mass times the acceleration of the 2 kilogram so you get a third equation that says 0 equals 0. That doesn't help. And a fourth equation that says T minus 19.62 is equal to negative 2A. So again, I'm going to do basically what I did before to solve this. I'm going to take equation 1 minus equation 4. So we get T equal to 5A, and the negative of this says negative T plus 19.62 is equal to positive 2A. So you get 0 plus 19.62 is equal to 7A. And so what do you get for A? 2.803 meters per second squared. This is the acceleration vector of the 5. This is the acceleration vector of the 2. All you have to do is plug in the value for A, and you get that the acceleration vector of the 5 is equal to 2.8030. Okay, so here's a question. Without solving it, we'll solve it in a second. What would you expect about the tension in that cable? Well, you look at this, look at the drawing, and it might be natural, I think it is natural to most people to think, well, that cable tension is caused by the weight of this 2-kilogram block. So it kind of makes sense that that cable tension would be equal to the weight of that block. But that's actually not true. And the reason that it's not is because these are accelerating. If these were at rest, the tension in this cable would be equal to 19.62. But since it's accelerating, it's actually, well, let's just do the calculation. It's not equal to the weight of the 2-kilogram box because the 2-kilogram box is accelerating. So plug this value back into, so the tension from this equation here, the first one, is going to be T is equal to 5 times this. So what do you get if you multiply those? .015 meters per second squared. No, that's a fourth. Okay, so if they were at rest or moving with a constant velocity, the tension in that cable would be the weight of the 2-kilogram, which would be 19.62. Since they're accelerating, we get a cable tension that's different from that. Okay, so here's a question. And I think this is something that confuses some people. You've heard about the term Pulley Advantage. You kind of have this vague idea that you can use pulleys to reduce the tension required in a cable to lift a big thing, right? But what I just said with this is that a pulley actually doesn't do that. All a pulley does is redirect that tension force. So how do you square that idea of pulley advantage with this definition of what a pulley really does? So then what's pulley advantage? Well, if you string up more than one pulley in a very specific way, you can get that effect. So if you string up multiple pulleys in a specific way, you can use the fact that pulleys redirect force. To actually reduce the force required to lift an object. And so here's how you do it. So if this is the thing you're trying to lift, let's say it's 100 kilograms, you attach that 100 kilograms to a pulley, but that pulley isn't attached to anything. That pulley is just hanging in the air. And then you make the cable go over another pulley that's attached to the ceiling or something solid. And the other end of the cable attaches to the ceiling. And now we're going to measure what's the cable tension required to lift this object. Okay. Well, if all we had was, so if this hanging pulley wasn't here and we just had the 100 kilogram mass attached to one end of the cable that went over a pulley and you're just pulling on the other end, the answer is to hold this up in the air, no acceleration, that tension would have to be equal to the weight. But we're going to see that actually with it rigged up in this specific configuration, that tension T is going to be half of the weight, which is pretty cool that it, I mean, you look at it and when I go through it, I think it'll feel like, we must have made a mistake or something, but you can actually take pulleys. We can do this in lab next time. Hang pulleys up in this configuration from like a coat rack or something, and you can actually feel how easy it is to hold up heavy things. So let's go through the calculation. So I'll do a free body diagram of the mass and the hanging pulley. Okay, so there's the mass. There's the hanging pulley. And just to make it clear, just to make it easier to imagine the direction of these cable forces, I'm also going to include a little bit of that cable in my, I'm going to isolate a little bit of the cable. So that's what these bad ears are. I'm including all of the cable going around the bottom of the pulley, and the hanging pulley, and the mass. Okay? And now the forces acting on this system are 100 kilograms times 9.81 down, so 981. And now where is there contact between the outside world and the boundary of what we're isolating? Yep. Yep, on each of those two bat ears, like coming out of the stump of cable, there's a cable tension in both of those. And since that cable is just going over pulleys, these are both the same. So we have a T here and a T here. And so Newton's second law says 0t plus 0t plus 0 negative 981 is equal to the mass, 100, times the acceleration. We're just figuring out what it takes to hold this up. So let's make this 0 acceleration. It's at rest, or moving with a constant velocity. So equation 1 says 0 equals 0. It's reassuring. And equation 2 says 2t minus 981 is equal to 0. So t is equal to 490.5. So with that way of rigging up a pulley system, the force required to lift that mass was cut in half. It's pretty cool. And actually, you can rig up systems with tons of pulleys. You start to get an added friction effect, so eventually it's not helping you anymore. But with this analysis, it says that for every new hanging pulley you add, you split the weight up into two more cable tensions. So, like if you had this, if instead of one hanging pulley here, you had 4 of them. I'm not going to do this calculation, but you'd end up with 981 divided by 8. So that's pulley advantage. And it doesn't come specifically from what a pulley does. It comes from a way you can rig pulleys up. You can take advantage of what they do in a specific configuration. Any questions about that? Okay. So here's an example that I'd like you to work on. I'll put this up and you can do it on the board. So let's say that we have a 4 kilogram mass and a 10 kilogram mass connected by a pulley. What's the acceleration vector of the 4 kilogram mass? And B, what's the cable tension? So yeah, everybody did that great. So what we know is that the acceleration vector of the 4 is equal to, we'll call that 0a, and therefore the acceleration vector of the 10 is going to be 0 negative a. Draw a free body diagram of the 10. You have a weight of 98.1 and a cable tension T. So Newton's second law says 0T plus 0 negative 98.1 is equal to 10 times the acceleration of the 10, so that's 0 negative a. And so our first useful equation says T minus 98.1 is equal to negative 10a. And then free body diagram of the 4. There's a weight of 39.24. A cable tension of T. So Newton's second law says 0T plus 0 negative 39.24 is equal to 4 times the acceleration of the 4. That's the one that's 0A. And so your second useful equation says T minus 39.24 is equal to 4A. And now this is a system of two equations for two variables. You can solve it however you want. And you get that T is equal to 56.1 and A is equal to 4.2. And then, in other words, the acceleration of the 4 kilogram, you can plug this back into your expression for the acceleration vector, wherever that was, here. And you get 0, positive 4.2. Any questions? Okay. We're going to cover one more thing today, and that is friction. So friction deals with objects that are sliding relative to each other. One of those objects often is the ground, but it can be two blocks or two whatever. But objects that are sliding relative to each other have two types of force acting. Bless you. Let's say they are acted upon by two force types. The first is they're in a pushing contact with each other. That's what we call the normal force. And the reason it's called the normal force is normal means perpendicular, and it's perpendicular to the surface of contact. And second is friction. And the friction force acts parallel to the surface of contact. Well, we know how to deal with that pushing contact. Now we have to talk about that friction contact. And this friction depends on the normal force. So the variable that represents the normal force is going to appear in our calculations of this friction force. And it makes sense if you think about, so right now, if I push on this thing on the table, there's a certain amount of friction force that right now is keeping it from sliding. But it can generate a lot more friction force to keep it from sliding if I lean on it, right? Intuitively, you know that's true. If I lean on it and try to push it, it takes a lot more to push it, you know? So what's happening there is that I'm increasing the normal force by pushing down, and that in turn is increasing the friction force. Okay. Okay, there are two types of friction force. The first one is called static friction. This acts between objects when they're not moving relative to each other yet. So when objects are at rest relative to each other, this is the friction that keeps the objects from starting to slide. This friction force has the magnitude required to prevent acceleration up to a maximum of a coefficient of static friction times the normal. The direction of this force is opposite what the acceleration would be without friction. Okay, so let me do an example. So let's say you have a box, it's 10 kilograms. And let's say you're pushing down on the box with 20 newtons and pushing this way on the box with 40 newtons. And the coefficient of static friction is equal to 0.4. So first, what's the force of friction required to prevent motion? And second, is that possible with this coefficient of friction? Okay, so a free body diagram. We have a weight of 98.1. We have these two external forces, the 20 and the 40. The ground's pushing up on the block, so there's the normal force. And which way is the friction force acting? So, yeah, the question is, which way would it accelerate if there was no friction? It would accelerate to the right, so that means the friction force is to the left. Okay. So I'll just put that in here like this. And now Newton's second law says 40, 0, plus 0, negative 20, plus 0, negative 98.1, plus 0n, plus negative ff 0 is equal to, well, we're trying to figure out what's the force required for this to stay at rest. So we're going to assume that it's at rest and calculate what that force is. So 10 times an acceleration of 0, 0. So we get two equations. The first one says 40 minus FF is equal to 0. So FF is equal to 40. And we can use that to answer part A. This is the force vector provided by friction. And so we can take this 40 and plug it back in there. So what do we get for a friction force vector? That's right. So even though we got a positive value for this variable, plug it in here and you get a negative component. And then the second equation says negative 20 minus 98.1 plus n is equal to 0. So n is equal to positive 118.1. Okay, so the second part of the question asks, with the coefficient of static friction that's given, is this friction force that has to be provided possible? Well, the maximum friction force is the coefficient of static friction times the normal. So that's 0.4 times 118.1. Can someone calculate that? It's more than 4. What is it? 47.24 newtons. So would this thing stay at rest or move? It would stay at rest because all that's required for rest is 40, and this friction is good up to 47. Okay? So the object stays at rest because only 40 newtons is required and the force of friction can go up to 47.24. Any questions about that? Sure. Okay, so that was the first type of friction, static friction. The second type is kinetic friction. That's when objects are sliding, moving relative to each other. And the friction force when the objects are moving relative to each other is equal to the coefficient of kinetic friction times the normal. And the direction is opposite the direction of motion. So opposite the direction of the velocity vector. So notice that in this case, in kinetic friction, the force of friction isn't up to a maximum. It's always the same thing. It's always equal to mu sub k times the normal. Okay, so as an example, let's say that, again, we have a box sliding along the floor. Let's say there's 30 newtons applied. It has a mass of 10 kilograms. And let's say that at this instant, the box is sliding this way. So that's the direction of the velocity vector. All right, well, first of all, is this possible? Could this happen? Like, what's making the motion happen going to the right if the force is applied this way? That's right. That's exactly right. So the idea is an object's velocity depends on all the stuff that happened up until that instant. And we don't know what happened before that. There could have been gigantic forces pushing it for half an hour, getting it up to really high speed right up until this instant. And right at this instant, that force disappeared and this new one started. But that object would still have that leftover velocity from before. Okay? So yeah, this is possible, even though obviously that velocity wasn't caused by that 30 Newton force. Okay, so let's calculate the acceleration of the box. There's a weight of 98.1. There's the applied force of 30. There's the normal force. And then what's the direction of the friction force? To the left, because it's just always opposite the direction of the velocity vector, direction of motion. And this time, we don't have to write this as an unknown force of friction. I didn't give a coefficient. That has to be given in the problem here. Let's say that the coefficient of kinetic friction here is 0.1. Now, instead of writing this as an unknown force of friction, we can write it as 0.1 times the normal, because we know that it has to be that in kinetic friction. Okay, so Newton's second law says negative 30, 0, plus negative 0.1 n, 0, plus 0, negative 98.1, plus 0 n is equal to the mass times, what do we know about the acceleration? It's all horizontal, so we'll just write it as A0. Even though actually you can look at it and tell that the acceleration's going to be in the negative x direction, but we don't care. That'll come out on its own. All right, so can we solve this system? Two variables, two unknowns, so we can solve it. The easiest way to do it is take the second equation. It tells you that the normal is equal to 98.1. And then plug that into the first equation, and you get negative 30 minus 0.1 times 98.1 is equal to 10a. So negative 39.81 is equal to 10a. So a is equal to negative 3.981. And then if you want that as an acceleration vector, you can plug that variable back in here. So the acceleration vector is equal to negative 3.9810. Any questions about that? One thing to notice about these coefficients of friction, can you tell from the equations what the units are of these coefficients? You know, coefficients can have units. Does this one? That's right, it doesn't. And the way you can tell is that you have a force, so this is in units of newtons, equal to something times another force, units of newtons. So the thing that it's multiplied to can't have any units. So the coefficient of static and kinetic friction are unitless coefficients indicating the amount of friction between two surfaces, or amount of friction between two smooth materials. So, for example, you could look up the coefficient of kinetic friction between steel and glass or something. You know, that those two materials have a certain characteristic friction between them, and that's represented by the coefficient. And second, the coefficient of static friction for two given materials is always bigger than the coefficient of kinetic friction. And you know that from like moving heavy cardboard boxes around. If you've ever helped move someone or anything, it's a lot easier to keep something sliding than it is to start it sliding. And that's because when things are at rest, there are molecular interactions between the floor and the object, or between the two objects that are sliding. There's like a stickiness that develops. And then you have to break those molecular bonds to get it moving. Once you've broken them, it's easier to move. So you can always get more static friction than you can kinetic friction. One application of that fact is anti-lock brakes. So what's the point of anti-lock brakes? The point is that if your tires are not sliding against the pavement, you can get a much stronger friction force than if your tires are sliding on the pavement. That's because the coefficient of friction between rubber and concrete is much, it's a much bigger static coefficient of friction than it is a kinetic coefficient of friction. And as soon as your tires start to slide, you switched into that lower kinetic coefficient of friction, and you don't want that. Okay, so here is an approach that we're going to use for sliding and rolling problems from now on. So, for example, say that you have a box on this surface and 50 Newton force applied. The mass is 5 kilograms. Let's say this angle's 20 degrees. Let's say the motion is down and we want to calculate the acceleration. What we're going to always do is use a coordinate system with the y-axis straight out of the surface. And then the x-axis has to be parallel to the surface. It simplifies several things, several quantities. First, the normal force is now always just going to be 0n. Okay, so that's great. We don't have to worry about I mean, if we use the, let me draw this coordinate system. If we use the coordinate system with x horizontal and y up, we'd have to use sine and cosine to represent the normal force. But now we have this nice, simple form. Okay. The acceleration vector can always be written A0. Okay, so that's nice. The friction force only has an x component. So that could be FF0 or negative FF0. You know, you don't know which way it's going. But still, that's a nice simple form. There's one trade-off for this. You know, we get all these benefits, and that's why we're going to do it. But there's one trade-off, and that is that the weight, which has always had a nice simple form, now we have to use trigonometry to represent that. So representing the weight gets messier. So let me just do this one example problem. Okay, so what forces are acting on this block? Yep. So that's 49.05. And then there's an external force of 50 newtons this way. Then there's a normal force. And then the friction force is opposite the direction of motion, so the friction force is acting up the incline. And we know that that's equal to, I forgot to give this coefficient again. So let's say the coefficient of kinetic friction is 0.2. Then the force of friction vector is 0.2 times n. Okay, so Newton's second law, using that rotated coordinate system, what's this 50 Newton force in the rotated coordinate system?
50.
Yep, that's just 50, 0. Nice and simple. The normal force is 0n, like always. The friction force is in the positive x direction in this case. Deal with gravity in a second. The mass is 5, and the acceleration we're going to write as a0. But what about the weight? Well, the weight is equal to 49.05 times, what's the angle here? Well, one way you can think about that is if there's your coordinate system with the positive and negative axes, then this angle is 20 degrees. And so if it was on that green negative y-axis, that would be 270 degrees. So this is going to be cosine of 250, sine of 250. So can someone tell me this? The second equation says n plus, what's 49.05 times sine of 250?
Negative 47.6.
Equals 5a. Nope, that was the second equation, so that equals 0. Oh, okay. Minus what? Okay. And so the normal is equal to 46.09. And then plug that into the first equation. You get 50 plus 0.2 times 46.09. What's 49.05 times cosine of 250? 49. I wrote this wrong here. It should be 0.05. So what do you get for 49.05 times sine of 250?
The other one, I think, should be minus 16.7. Why?
It should be the big one. So is this 16 point?
This is the 49.05 times cosine of 250 is minus 16.776.
16.776? Okay, so plug that in. I know you guys got to go. Calculate A. All right. So I'll post homework for this week, and please use this week to read through notes, work through example problems, and all that.